Pre-statistics, Residual Analysis, Part 4. Using the data and functions from example 4, compute the residuals for each function for the year 2014. Our first step for this problem, we need to compute what is t, and t is the number of years since 1790. So if we take 2014 and subtract 1790, t is 224. In order to compute the residual, we need to know what is the observed population for the year 2014, or for the year t equals 224. According to Google, the U.S. population in 2014 was estimated at 318.9 million. So this is going to be the value of our observed y value. So if you recall, we have our linear function L of t, our quadratic q of t, and our exponential e of t. And we will compute the predicted y value for each of these three models when t is 224. y1 is L of t, the linear regression, y2 is the quadratic regression, and y3 is the exponential regression. Now we can find the predicted value a couple of different ways. The first way is I'm going to use the table feature. First, I just want to double check this. I'm going to graph it with the data set and make sure I didn't put in a typo and it models the data correctly. So I'm going to go to zoom, number 9. There's the linear, there's the quadratic, and the last one there's the exponential. The exponential, according to scatterplot, is doing the best job. So that looks good. If I hit table, I have y1, y2, and if I move my arrow over, I can get the exponential, y3. Since we want the x value to be 224, I need to go to table set, which is second window, and I want it to start, let's say, 220, and I want to count by ones. That's correct. So let's go back to table, second graph. When t equals 224, the linear model is predicting 84.72 million. The quadratic is estimating 254.71, and then the exponential was 2,971.01 million. There's another way that we can compute the predicted y value without using the table, and that's using the variable key, the vars key. So if I hit vars and go to y vars, then number 1, that's our linear function, hit enter. I can hit parentheses, type in our t, which is 224, hit enter, and we get the 84.72 million rounded off. For the quadratic, I go back to vars, y vars, number 1 for function. This time we want y2, which is number 2. Again, parentheses, put your input, 224, and hit enter. And we have 254.71 million. And lastly, the exponential is in y3. And the exponential is very large, 2,971.01 million. Now let's compute our residuals. To compute the residual for the linear equation, if you recall, the residual is the actual y value, which was 318.9 according to Google, minus the predicted, and the predicted for the linear was 84.72 rounded off, and we have a residual of 234.18. So clearly the model underestimated the population in 2014. The residual is a positive number, so there was a underestimate. For the quadratic, we take 318.9 million and subtract 254.71, and this model missed it by 64 million. And then the last one, if we take 318.9 minus 2,971, clearly this is the worst prediction. This is going to be the worst residual. We have a negative 2,652 million. So since the residual is negative, the model overestimated. So when we create regression models, the model is usually only as good when it is near the domain of the x values. And since in this example we're looking at the population to 1660, we extrapolated the data way too much for actually any of these models to be reliable. So for the limitations, we need to keep in mind about the interpolation and the extrapolation. If you recall, the interpolation is when we use values that is in the domain of our x coordinates. When we extrapolate, we are using values outside our domain, and the models are only guesses. We assume that the pattern continues, but it may not. So this is a big limitation to a regression model. It is best that we interpolate whenever we can. When we extrapolate, we very well could be incorrect. And here we have our last demonstration of residual analysis. In the previous video, the question was asked, why don't we just look at the r-square value and say whatever function has the highest r-square value, that's going to be the best function. Well, actually we need to look at all three concepts. We need to look at the scatter plot of the data, the x variables and the y variables. We need to look at the value of r-square, and we need to look at the residual plot. We have 4 different data sets here. Clearly they're different, and if we were to take the time and plot the scatter plots of these 4 data sets, we would have 4 different patterns. Here we have roughly a linear pattern. This is a quadratic pattern. Here we have almost a perfect linear pattern, but we have one point that is away from the rest of the data. In statistics, this is known as an outlier. And then here we have a number of points that all have the same x values but different y values, and another outlier. It turns out that if we computed the r-square for the first scatter plot using the linear regression, we would get r-square of about 0.67, about 67%. If we did it for this data set, we would get exactly the same value. If we did it for the third data set, r-square would be exactly the same value. And even for the last data set, we would get exactly the same r-square. So this is why it's important that we look at all 3 concepts: the scatter plot, r-square, and it's also a good idea to look at the residual plots. Thanks for watching.